Hi guys, today I want to talk about uncompetitive inhibition. Inhibition in enzyme kinetics. Okay, so what does uncompetitive inhibition look like? You have an enzyme and substrate, and let's say you have a reversible reaction to form the enzyme substrate complex, and again the enzyme forms and the product forms. This is the standard Michaelis-Menten kinetics. So it's K1 forward, K minus 1 backward. This is the standard one, right? Okay, so now let's say you have an inhibitor and it only binds to the enzyme substrate complex. And well, sometimes you'll have this thing called non-competitive inhibition where the inhibitor binds both to this and to this. But this time, in this uncompetitive inhibition, well, you get the idea that it's even less competitive than non-competitive. So in a sense, you can use that to remember this thing only binds to the enzyme substrate complex, and again one forward and one backward. So let's name this Ki small, K minus I. So there's the inhibitor equilibrium. Then you have this ESI complex. Okay, so moving on, how do we derive the usual equations? Well, as usual, we have our mass balance. So V equals to dP with respect to time. And this is equals to K2 into ES. That's always the first equation, because this is what you want to know, and you trace it back. This is the immediate substance, the enzyme substrate complex, the immediate chemical that's actually going to form your product. Okay? And so, how about the ES balance? So the ES balance will be minus K2 into ES plus K1 into E and into S minus K minus 1 ES. Okay, and then plus K minus I into ESI close plus Ki to ES and I. So okay, let's break it down. Yeah, the forward reaction is this, and it's a negative effect on the ES balance. The backward reaction for this K minus 1 is here. The forward reaction is this term. This represents the backward reaction. Okay, and this term represents the forward reaction. And that's our rate of change of ES with respect to time. And third, of course, you have the enzyme balance, where you have the total concentration of enzymes, which equals the total concentration of free enzymes plus the enzyme substrate complex plus the ESI, enzyme substrate inhibitor complex. So these are your three basic equations. You always start with this for Michaelis-Menten. And of course, what's next? What's next? You have to assume either quasi-steady state or rapid equilibrium. In other words, which reaction is rate controlling. So, okay, for simplicity's sake, we'll just assume the rapid equilibrium. So this reaction is controlling. So always you'll have these two in equilibrium. So, okay, we will go with the rapid equilibrium approach. This is assuming this is controlling. And what do we do with that? Rapid equilibrium, what does it mean? That means this thing and this thing cancel out. this and this cancel out because it is already at equilibrium. Okay? And you have ES going as an exponential trend, I suppose. Yeah, so anyway, the forward and backward rates are pretty much the same. That's why I'm cancelling them all off. Okay, so that leaves us with this and this, which may not be that helpful. So we have to look at this. Okay, we have to look at this because this equation is not going to help anymore. So this is a constant. This is what we want to substitute into this equation here. So let's rewrite equation 3. So equation 3 is ES equals E naught minus E minus ESI. Close bracket. So what is ESI equals to? So what is this? Let's go with that. So under equilibrium conditions, you have the Ki into E, ES, and I, which is the forward reaction of this and the backward reaction of this. I'm going to put them equal to each other. ESI, and I'm going to divide by Ki, the forward rate. So ESI equals to, so I'm going to divide, then I'll just have this big K, this big Ki equals to K minus I, or K, small Ki. So this is the equilibrium constant. So big Ki into ESI. So ESI equals to these two over this. Okay? Right, so let's do ESI equals to ES and I over Ki. So in fact, we assume that in inhibitor concentration is like, roughly constant. And let's substitute this in here. Wait, no. The inhibitor concentration is not constant, but it can be measured. This can be measured. So we are just going to leave it down there. So let's put this. Okay, that's one part solved. And what do you have to do with the other part? Well, let's bring this paper a little bit more to this part. Okay, so you have this, and you have the, let's just write for clarity's sake, E naught and E. Okay, so what is this? What can we use to substitute in to our equation? We probably want to look at the other equilibrium, which is the K1 into E, K1 into E into S equals to K minus 1 into ES. Okay, so I'm going to bring this over again. So that will bring the big K1 into ES, where this big K1 equals to K minus 1, the small K minus 1 over the small K1. So that will be E into S, and then I'm going to make ES the subject, and there you go. Pretty simple. So, oh, right. We're supposed to make E the subject. So let's make E the subject instead. My apologies there. So let's bring K1 to the left-hand side. You have ES, and you divide everything by S. Okay? So let's bring this here. So you have E naught into, oh sorry. So this is the next line of the equation. So E naught minus E, which is ES over S times big K1 minus ES into I over Ki. Now let's bring this over to another page so it's neater. I'm gonna shift this around here so it's a lot easier to see. Okay, so let's write down that equation again. ES equals to E naught minus E minus the concentration of ESI, and that you will write it as, well, you have previously just substituted the big K1 into ES over small s, the substrate. Then you have ES into I over Ki. So there's no mistake there, it's really like that. So ES. Now let's bring these two terms over so we can start factorizing ES out. So ES, so we have 1 plus, this one you bring over, it becomes a plus, K1 over S, big K1 over S. This one you bring over, it also becomes a plus. Then you have I over Ki. So the inhibitor concentration over the uncompetitive inhibitor constant. And then the whole thing equals to E naught. And with that, ES should be pretty easy to find this time. K1 over S, this is the first one, plus I over Ki. Now we can substitute into our first equation, which is this. V equals to dp dt, K2, which is K2 into ES. Now we can just substitute everything wholesale. K2 E naught over 1 plus K1 over S plus I over Ki. Yep. So, well, to make it into a more familiar form, let's define the Vmax again. Equals to K2 E naught, and that will equal Vmax over 1 plus K1 over S plus I over Ki. And we just, to make it familiar to our usual Michaelis-Menten equation, we multiply S to the bottom and top, bottom and top. I over Ki. Okay. So let's multiply that in. So you have S plus K1 plus I S over Ki. Well, almost there. Only thing is that S is still inside in a sense. Yeah, this S is still inside. So it's not really looking that similar to our usual Michaelis-Menten equation. Okay. Yeah, but this is, well, it looks kind of similar to a KM apparent. However, this is probably not what we want, because this thing actually varies with S. So we want to have it in such a way that it does not vary with S. Okay, I will stop here for now before the video gets too long. In the next video, we will continue more on uncompetitive inhibition. Shall see you guys next time. Bye bye.